thank you first of all for the invitation to come here. It's always a pleasure to be here and to give these lectures. And I have lots of things to tell you about, and hopefully this 8 hours will be enough. So let me answer first Frank's observation. Let me make a more precise title for these lectures. So let's call this global, let's say, well-posedness conjectures for, let's say, dispersive equations, for nonlinear dispersive equations with non-localized data. So this is all about recent joint work with Mihaela Ifrim from University of Wisconsin. And so just to get started, we have lots of classical conjectures in PDEs, and my talk will not be about any of these classical conjectures. Perhaps it's time to have some new sets of conjectures for the young people to work on. So that's one way you can look at it. Another way you can look at it is that this is what might happen to mathematicians in a pandemic with too much time on their hands. Might come up with some new conjectures. And so to get started, let's take a nonlinear PDE. I'll make it first order in time with some expression in here that we want to be nonlinear, and we put some initial data to this. Let's say our evolution happens in R cross Rn, so time and space dimensions. All right, and then we put our initial data in our favorite Sobolev space. And then we look at solutions to some equations of this form. Of course, not the most general equations. I'm going to specialize in a moment. But in PDEs, there are some classical questions that you can ask once you see some equation. And maybe one question to start with is the question of local well-posedness. And you all know what local well-posedness means. Means you want to have existence, uniqueness, and continuous dependence on the initial data, Hadamard style. And then maybe one subproblem, if you want here for local well-posedness, is to also ask for local well-posedness at low regularity. So here you perhaps try to understand what happens when your initial data is really rough, whether you might still get solutions for your favorite equation. And that's not the problem that we were initially interested. We were interested in the problem of global well-posedness. And so this has to do with the fact whether your solution lasts for an infinite time, perhaps both forward in time and backward in time. Now, usually when you talk about global well-posedness, you might not even be able to prove global well-posedness results without being able to say what happens with the solution for a very large time. So you want to perhaps understand asymptotic behavior of the solutions. And one word that is used often in this context is the word scattering. And later today I will tell you about the various meanings that we give to this word. Now, when you look at global well-posedness in many problems, one makes a difference between small data and large data. And of course, you want to understand first what happens with the small data. Finally, one other distinction that you can make in here is how does your initial data look like? And two very simple alternatives that you have in here are, one, you could look for concentrated initial data, or you could look for arbitrary initial data in your favorite Sobolev space. And we call this localized versus non-localized data. And to give you an idea about the path we follow in this grand scheme of things, we are interested to start with in the global well-posedness, and this gets back together with the question about the asymptotic behavior of the solutions. We're not at the large data stage, so we'll worry only about small data. All right? And in terms of localized versus non-localized data, we're interested in problems with non-localized initial data. So any HS function is an admissible candidate for your initial data. So this was sort of our original goal. A posteriori, after learning more about these things, eventually this global analysis turned back, and we were able to return to the question of low regularity local well-posedness and get some very interesting results there. And then we cycle back again, and then we want to have this global well-posedness results at low regularity. Okay? So that's the game plan. And as the title says, we're looking at nonlinear dispersive equations. And the dynamics of nonlinear dispersive equations, you can think of them as the combination of two factors. The first of which is linear dispersion. And so when you look at corresponding linear flows in dispersive equations, you have maybe two essential properties. First of all, you have propagating waves. So for instance, you have no diffusion, no damping in the equations we're looking at. And secondly, these propagating waves, they propagate with different velocities. So waves, let's say, with different frequencies have different I'd say velocities, but let me add one word in here, group velocities. All right? I'll get more specific in a moment. And secondly, you have nonlinear effects. Which means that these waves that before were propagating linearly are allowed to interact. Okay, so linear waves can interact. And so when you look at nonlinear dispersive equations, the game is played between, if you want, dispersive decay So here's a new word, decay. And this happens because of the dispersion. You have waves that move in different directions, so eventually you'll get some decay in there, versus nonlinear dynamics. All right? And if you have a game with 2 players, you can think of 3 possible scenarios. And the first, and maybe the easier scenario, is that is when dispersive decay is stronger, in which case, especially if you put your initial data to be small, you expect that the dispersive decay would win because it would get to act before nonlinear dynamics, all right? And then you would expect your solutions to look very much like linear waves over long time scales. The second scenario, and then the third scenario, let me skip to the third scenario where nonlinear effects are stronger. Right? And of course, in the middle, we're going to have the balanced case, where the linear effects and the nonlinear effects are just as strong. All right, so the class of problems which has been most studied in nonlinear dispersive equations, as many of you know, is the first class in here. And of course, many problems here have been solved, though not all. So our interest was to take the more difficult class of problems and look at what happens for problems when nonlinear effects are stronger. All right? So that's one of our targets. And our second target, we take a step back, and we also look at problems where we have we have a balance between linear and nonlinear effects. And maybe when we go back to balance, we can make a distinction between 2 classes of, if you want, nonlinear equations. There's a class of nonlinear equations that we call semilinear. And then we have quasi-linear problem. Quasi-linear problems are more difficult to study. And in the balanced case, specifically, we're interested in quasi-linear problems. So in the balanced case, maybe many semilinear problems also have been studied, but not quasi-linear problems. And in terms of looking for global solutions for dispersive waves in this context in here, basically until a couple of years ago, there were no results whatsoever, essentially. And so what we wanted to do is we wanted to come up with some predictions as to what one might expect to happen for this kind of flows. And that's our conjectures. And then, well, you can make conjectures out of the blue, but it's always better when you can prove those conjectures in some cases. So then we wanted to be able to prove these conjectures, at least in the simplest cases. In some sense, the conjectures that I'll show you, maybe sometime today, are very broad conjectures. They apply to essentially an infinite number of equations. So there is no such thing as proving one of those conjectures. There is such a thing as proving those conjectures on your favorite model. Okay, and so it's open season on proving those conjectures on specific models, and maybe now is a good time to tell you about what is my game plan for this lecture. So, of course, the first goal is to give you enough background to motivate these conjectures. And describe the conjectures. And this will take pretty much all of today's lecture. Maybe
Daniel, with Nicolas, we ask ourselves a question. The solitons, are they in 2 or in 3?
I will answer this question in detail during the lectures. Yes, that's indeed one of the important questions you need to ask yourselves when formulating these conjectures, right? So I want to describe these conjectures. Number 2, to give you an overview of the results so far. Three, to provide you with a good set of tools that we have created to prove these conjectures in some cases, or to show the involved in proving the conjectures in some cases. And finally, as I promised, to loop back and show how these ideas help us sort of reinvent a little bit the study of some of these problems at low regularity. So maybe apply these ideas to low regularity well-posedness. All right, so like I said, this is all joint work with Mihaela Ifrim. If you want to read about this, at this point we have about 6 papers on the archive. Of these 6, 1 is expository, so that might be a good place to start. This is now at the beginning of the lectures. By the time I'm done, there will be 7. So it's an increasing number. All right. So far this has been sort of a very broad introduction without any formulas. But of course, we're mathematicians, we want formulas. So I'm getting to that. Once I figure out the erasing tools. Works. So let me start with an equation. And just to keep things simple, I'll write an equation just as in my previous model, something that's first order in time. So I dt minus a of d apply to our solution u is a nonlinearity, which depends on u and derivatives of u, so on. This operator in here, this on the left, we have the linear part of the equation. This is the nonlinear part. We're looking for complex solutions to this equation because we have this I over here. And so this means that really in pretty much all models, you have two objects to worry about. You have the solution u and its complex conjugate, right? So when you talk about this nonlinearity, this is really a function of u and u bar. Okay, so you might have various combinations of u and u bar, and I'll discuss this in greater detail later on. In terms of the object that we put in here, I think of this as a smooth function of u and u bar and their derivatives. Some of the models we're interested in are non-local, so this doesn't have to be a local operator. And then it also does not have to be weaker than the principal part. So naively, you could think of quasi-linear equations where the nonlinearity has the same strength as the principal part, semi-linear where the nonlinearity has weaker strength than the principal part, but just very naively. All right, so let's begin with the left-hand side in here. There's the minus in here, which is just a notation, just for convenience, right? This is a standard notation. And then a of d is a multiplier. So it's a multiplication by a function in the Fourier space. When we have multiplication by a function in the Fourier space, we have a name for that function. Let's say a as a function of the Fourier variable xi is what we call the symbol of a. And often this a is called a dispersion relation. Okay, and maybe the other important thing that I should say in here is that when we talk about dispersive equations, I was talking about the velocities of waves before. So for each frequency xi, we have a group velocity vxi of the waves with frequency xi, and this is the gradient with respect to xi of a. All right, and then the next question to ask is, well, does this really depend on xi? And so far we have been looking in problems with full dispersion. In other words, where this fully depends on xi. So full dispersion corresponds to the Hessian of a to be non-degenerate. I'm not asking for any uniformity in here. This is just a qualitative property that tells us that at around every frequency, you spread out to the maximum extent that's allowed. All right, so this is our sort of linear model, and maybe let me give you some examples. And of course, the first example that I should put in here is the Schrödinger example. So a of psi is equal to psi square. Maybe a next example could be psi cube. That's one dimension. That corresponds to KdV type models. Then, since I'm writing equations first order, the next example could be square root of 1 plus psi square. So this is half Klein-Gordon waves, if you want. Let's see, what should I go on with? A of xi is equal to, let me just write the functions, c to the power 1/2. So these are gravity waves in deep water, c to the power 3/2, capillary waves in deep water, square root of psi hyperbolic tangent of psi. These are gravity waves in shallow water, square root of psi 3 hyperbolic tangent of psi. So capillary waves in shallow water. You can tell from these examples that some of our interest here came from water waves. Maybe to move away a little bit from water waves, another equation that we've been interested in is what's called the SQG front equation, and that corresponds to psi log psi. All right, so what I want you to take away from these examples is that there are indeed many classes of dispersive equations, even more so when you allow for non-local operators in here, and we want to allow for non-local operators in our conjectures. And also that fluid dynamics is a great source of problems of this type. All right, so these are maybe the models, some of the models that we have in mind. And now, I'll still stay with the linear part of the equation for one more board. And so maybe now we want to look at how do we measure dispersion. And of course, you all know maybe many ways of doing this. Maybe this first thing that you come across is what happens if you start with a localized data or with the Dirac mass. In the case of a Dirac mass, of course, you have the fundamental solution. So for instance, Dirac mass. The fundamental solution at time t would make a group which is e to the power I t a of d, all right? And if you want to find the fundamental solution, you would take the inverse Fourier transform of this. So k of t is equal to inverse Fourier transform e to the power I t a of d. When you write this expression, you get an oscillatory integral. And you can estimate that oscillatory integral using the method of stationary phase. And at the end of the day, you will come up with at least an asymptotic expression for the fundamental solution. And that would be something like k of if you want t and x will be. So first of all, from stationary phase, you're going to get some decay, 1 over t to the power n over 2. And so this decay essentially measures the number of degree of freedom for the decay. So we're in n dimensions. Our waves can spread in n directions. So that's what gives this decay. Then we have a phase, maybe so in many cases, for instance, A is convex, and then this phase is just a Legendre transform of your dispersion relation. And then you're going to have some amplitude. At leading order, this amplitude does not really depend on time. So it's a constant along rays. So decay phase and amplitude. And so this means that if you have localized initial data, then you're going to have some estimate for your solution, what we call dispersive estimates. Solution for the linear equation at time t, measure in L infinity, smaller than, let's say, t to the power minus n over 2, the dispersive decay, and then the initial data in L1, perhaps with some omitted stuff in front in here having to do with derivatives. Okay, so you have a bound from L1 to L infinity, and if you think about your initial data as localized, then your solution will have pointwise decay. All right, so this is just for completeness somehow, because as I was telling you, we're interested in problems with non-localized initial data. So then dispersive decay, uniform decay is out of question. And the reason for that is, let's say, move here. So 2, maybe non-localized data. So this corresponds maybe to U0 in an L2 type space. For the linear evolution, the L2 norm of the solution is conserved, so you can measure it at any time, and it's the same. So the time where you measure the data says nothing about the decay of the solution. So in this case, there cannot be any uniform decay. Unfortunately, we have a good substitute for this uniform decay. We have averaged decay. All right, and this average decay is what we call one of the measures of average decay is the Strickard's inequalities. And so here you try to measure the solution in some LP in T, X in Q. And depending on the dimension, you have a range of Strickard's exponents. And of course, the smaller the P and the Q, the more decay you have. So you want the smallest possible exponents. And those are given by sort of the theory of the restriction theorem, if you want. And the relation between these exponents P and Q is 2 over P plus n over Q is equal to n over 2. And then your typical Strickard's estimate will look like norm of the solution U for the linear equation in, let's say, LP, LQ is smaller than the norm of the initial data in L2. And depending on the problem you're looking at, here you might have some derivatives coming up. But in essence, you have, for L2 initial data, your solution in spaces of the form LP, LQ. Yeah, let me remind you a little bit the numerology for this exponents P and Q. In one dimension, this range of Strickard's estimates is between the energy bound, L infinity, L2. So I'm going to omit from here on T and X. Always the first L is in T and the second one is in X. And this goes all the way to L4, L infinity, what we call the Pecher estimate. The energy estimate, of course, will play an important role in energy bound in what I'm going to tell you. But the other important number in here, in between, if you interpolate, you have the L6 norm in space and time. And the L6 norm is the one that will play a fundamental role in one dimension. In two dimensions, we have L infinity, L2, and the L2, L infinity as the endpoints. This one comes with the usual asterisk, which means that it's forbidden, but we have the full interpolated range. And then right in the middle, we have the L4 bound. And in my story, the L4 bound will play an important role. And finally, I'm not going to tell you much about higher dimensions, but for completeness, we start at L infinity L2. At the other end, we have L2, L2, n over n minus 2. And right here in the middle, we have L2, n plus 2 over n. So this is taken on both x and t. All right, so these are the Strickard's estimates, a good way to measure dispersion, but not enough for our purposes. So our next way to measure dispersive decay in the case of non-localized initial data consists of what are called bilinear estimates. And specifically bilinear L2 estimates. Okay, and those of you who are familiar with the work around the restriction theorem know about the bilinear restriction theorem and know that bilinear restriction estimates are not necessarily in L2. For what I'm going to tell you, we're only going to work with L2 estimates. All right, and if I'm taking two solutions to a linear wave, let's say I want to give you an example in one space dimension, and in one space dimension we have the Fourier line, and let me take two regions here, A and B, and let me take two solutions, one which is frequency localized in this region A, and another one which is frequency localized in the region B. Okay, we'll do, so this is the red region, this one will be white, because I only have two colors. So the red guy will produce some red waves that move in some direction. Okay, I'll go with blue, thank you, Frank. The blue one will go in the blue direction, okay? And the important thing is because we have dispersion, the red waves and the blue waves will travel in different directions, and when they meet just once, all right? They meet, greet, go apart. And then this bilinear L2 estimates in one dimension, now I'll switch back to white, are estimates for the product of two solutions, UA times UB. And to confuse you, I'll put a complex conjugate in here. And so the product estimated in L2 is smaller than the product of the two initial data, L2 in L2. But of course, you'll have an implicit constant in here. What is this implicit constant in here? Well, this implicit constant is supposed to measure the transversality of these two waves. And so what you have in here, in effect, is the difference of the two corresponding group velocities to the power minus 1/2. So the closer the group velocities are, the worse the constant in here, and vice versa. All right, so we have these two measurements of way to measure dispersion, Strickard's estimates, and then we have this bilinear L2 estimates. And so this will play a role in my story. Now, I'm telling you how these estimates look like for the corresponding linear flow. Unfortunately, this is, for everything we do, this is always too weak to be useful. So this is just for orientation purposes, to get the numerology right and to get the types of estimates right. I skipped this board first time around. All right. This will not happen again. And by the way, so speaking of this L2 bilinear estimate, one way you can think about it, as a convolution estimate in the Fourier space, and this is a simple exercise I give to my graduate students so that they get to play a little bit with this convolution estimates. All right. So mistakenly, somehow I called both of these dispersive estimates. In effect, the Strickhartz estimates, they are measures of dispersion. The bilinear L2 estimates, they have nothing to do with dispersion. You should call them transversality estimates. They measure the transversality of two waves. It doesn't matter whether the two waves disperse or not. Okay? So you could have two transport equations going in different directions, and the estimate would still be true. It will be a lot easier to prove if those are two transport equations. Now, once we have this dispersive ways to measure dispersion, the other thing that's important is what is the worst case scenario. All right? The worst case scenario is kind of infinite in the context of the bilinear L2 setting, but we do have a well-defined worst case scenario for the case of the Strickhartz estimates. And this has to do with the notion of wave packets. All right. What are wave packets? You start with a very localized initial data for your dispersive problem. So your initial data is maybe some bump function, depending on the distance of x to the center. So think of this as a Schwarz function. This is a scale parameter. So x is localized on the lambda inverse scale. And then you have some phase. And so this means that you're localized. So this is centered at this point x naught. On the scale delta x is lambda inverse. Okay, and in frequency, you're centered around psi naught. And this happens on the dual scale. Delta psi is equal to lambda, and this is what we call the uncertainty principal scale, right? These are dual scales. And so you put this initial data, and you ask what happens to the corresponding solution to our dispersive equations. And what happens is that the initial data, well, the solution, because your data is pretty much localized at a certain frequency, will like to travel somehow with this group velocity. So you might expect that your solution U looks like some function of, let's say, maybe very mild dependence on t, and then lambda times x minus x0. x0 is not the correct object to put in here. We have to allow for transport by the corresponding group velocity. All right. And then we have a phase, xt. So this would be our xt, the position, the center of the packet, if you want, at time t, times psi0. Psi does not change. And then maybe an extra phase, I a of psi naught times t. All right? But this kind of expansion doesn't hold forever. It holds for a certain time interval. And you can easily compute that time interval. We just said that our packet is localized in position on the scale lambda minus 1. So instead of x0, you can move for a distance lambda minus 1 away from x0. So from the perspective of the group velocity, the position at time t should be equal to maybe x0 plus v psi 0 times t. This is where the center goes. But x0 is not uniquely specified. It can vary by lambda inverse, so plus O of lambda inverse. And then the frequency is also not very specified. It's specified only up to this uncertainty in here. Okay, so you add the change which is due to the change in group velocity, which is due to the change in frequency. So this is something like t times delta psi times let's say O of t times lambda, right? Lambda being the changing psi and t coming from here. All right, so the change in the initial position doesn't promote spreading of the packet, but the change in frequency does promote enlargement of the packet. And so then you just look at what is the time scale where these two guys balance. All right, and these two guys would be equal if t is like lambda to the power minus 2. So delta t is lambda to the power minus 2. This is wave packet, what is called the coherence scale. And the picture that you can have in mind in here, you have your nice bump initial data centered at the point x naught. It travels with your favorite group velocity up to this time, delta t. And once it gets here, it begins spreading out because it has a two large set of group velocities that it has to comply with. All right, so these are wave packets, and in terms of wave packets being sharp examples for Strickard's estimates, we only care about this interval of coherence. Once they begin to decay, you lose in the Strickard's measurement of the solution. And maybe I should also say that we have something else that's nice in here. We have what are called reverse Strickard's estimates, which say that, well, if you have an almost maximizer for a Strickard's estimate, then that almost maximizer has to have a wave packet inside it, roughly. All right? So this is really the only bad scenario. And we really care about these guys not from the perspective of actually using them in proofs, but we care them in terms of heuristics. You want to know what is your enemy, and this is our enemy in what I'm going to tell you in a moment. All right, so I told you a lot of stuff about the linear flow, and now I'm going to move on to the nonlinearity. Still, I have a little bit of ground to cover because before I can state the conjectures. So we want to classify nonlinearities. So this is just to establish terminology. And there's one way that we can classify nonlinearity, if you want, by the strength of the nonlinearity. So we look at semilinear versus quasi-linear problems. And here perhaps I should say that sometimes, I mean, when you start teaching a PDE class, introductory PDE class, you classify this by the way the equation looks like. But really the good way to classify this is by how the solution depends on the initial data. So for semilinear problems, those are the problems for which we expect to have Lipschitz dependence of the solution in terms of the initial data. And quasi-linear problems, we should call those problems for which we only have a continuous dependence of the solution on the initial data. And so, of course, semilinear problems will be easier than quasi-linear problems. Second, by homogeneity, let's call it K, the homogeneity. Let me begin with K is equal to 2 quadratic nonlinearities. And so here you might think of nonlinearities of the form, let's say C of U and U, or C of U and U bar, and C of U bar, U bar. This would be the three possibilities. Second, K is equal to 3. And of course, I'm not going to write down all combinations in here, but I'm going to write down the important combination. And the important combination is C of U, U bar, and U. And what's special about this combination, this is a combination that has one extra symmetry, which we call the phase rotation symmetry. In other words, if I replace U by u e to the power I theta, theta is a constant, a real constant, then the same transformation applies to the cubic nonlinearity. And next comes k greater than or equal than 4, that I'm not going to care very much about. And the reason for this is we're looking at small data problems. The larger the power, the weaker the nonlinear effect somehow. So those are the good guys with large k. And you might say the bad guys are 2 and 3. And then 3, we can classify nonlinearity by leading order effect. Particularly in the cubic setting with the phase rotation symmetry. And here you can have 2 leading order effects of the nonlinearity. You could look at focusing versus defocusing problems. I'll tell you a little bit more about this in a moment. All right. Now, to finish setting up the terminology, if you want, we can also, so this is about nonlinearities. How about the strength of the nonlinear interactions? So here we think of 2 nonlinear waves, and we fit them into the nonlinear equation. What happens to them? The first, if you want, way to classify this is by looking at the group velocity of the 2 waves. I should have taken the chalks. So one situation would be when you have waves which move in the same direction. So this would be parallel waves. And the other situation would be waves that move in transversal directions. So here you have parallel and transversal. And of course, the parallel interactions would be stronger, and the transversal interactions would be weaker, just based on how much time the 2 waves spend together. The other way to classify waves has to do with the phenomena of resonance. And this has to do with what happens when 2 waves meet. So we have the red wave, the blue wave, they meet. What happens in the nonlinear equation at this point? And there's an easy scenario. Nothing happens. You create a little, maybe localized bump in here, and then each wave goes its own way. And this is what we call non-resonant. The second picture, you have one wave, the blue wave and the red wave. And at the point where they meet, perhaps they generate another wave. And so this is what we call resonant interaction. And we can describe this algebraically when an interaction is resonant and when an interaction is non-resonant by looking at maybe the principal symbol of our linear operator. So if you have a solution to the homogeneous linear equation in the Fourier space, this solution is localized on the characteristic set of our linear operator. And so this would be, let's call it sigma, which is tau plus a of psi is equal to 0. Psi was the space Fourier variable, tau is my notation for the time Fourier variable. And so when you multiply 2 functions, their frequencies add up. All right? So you start with the red wave, one point on this surface, the blue wave, that's another point on the surface, and you ask whether the sum of the 2 vectors still ends up on the same surface. So you try to solve the following algebraic problem for resonant interactions. sigma plus or minus sigma is equal to, well, goes to sigma. And those frequencies for which this happens are resonant frequencies. If this doesn't happen, then they are not resonant frequencies. This is for two-wave interactions, and then you can generalize this to three-wave interactions and higher. All right. That concludes my description of the nonlinearity in the problem. And my next, the next question that we ask is, we said we want to try to describe problems where the nonlinear effects are stronger. When are the nonlinear effects stronger? Maybe I'll keep that board for the equation. And let's ask, when are the nonlinear effects stronger? And if you cheat a little bit, one way you can think about this is in terms of Strickardt's inequalities. So if I have a linear flow, so let's say I dt plus A of d u is equal to f, u of 0 is equal to u0. For this linear flow, you have Strickardt's inequalities. And one way you can write the Strickardt's inequalities is to say that norm of the function u in your favorite Strickard space of the one that we have on that board over there is smaller than norm of u0 in L2 plus norm of the nonlinearity of the source term in the dual Strickard space. And so you might say the linear effects are stronger if, or at least equal, if you can handle nonlinearities using this kind of estimates. And when I say handle the nonlinearities using this kind of estimates, I'm trying to be very naive. I don't want to worry about high frequency limits, low frequency limits, and so on. I just think of frequency of size 1, so there's no frequency in my picture. And then I'm looking at the map u goes into n of u, whether this takes S into the dual Strickard space S prime. Because if that's the case, I might think that I might be able to apply the Strickard's estimates globally in time. So can I do this? Well, this depends on the homogeneity of the nonlinearity, or alternatively on homogeneity and the dimension. So if we have dimension n is equal to 1, then Strickard space, maybe we could put here NL6. S prime would be L6/5. To get from L6 to L6/5, you need to have a fifth power, right? So k is equal to 5 is critical. If you take n is equal to 2, then you have L4 and L4/3. So here k is equal to 3 is critical. And finally, if I skip a bit, n is equal to 4, then k is equal to 2 would be critical. Okay? So reversing the tables, we could say, well, nonlinearity is stronger if k is equal to 2 in dimensions 1, 2, and 3, if k is equal to 3, if n is equal to 1. And then we have the borderline cases, right? So in essence, to understand this question that I'm posing, to understand the dynamics, the global dynamics of dispersive waves in regimes where the nonlinearity is stronger than the linear effect, I'm confined to these situations. Either look at quadratic nonlinearities or look at cubic nonlinearities. And then I have to do this in low dimension. For cubic nonlinearities, I also mention here n is equal to 2 is critical. So I will also care about this. So how do I choose between k is equal to 2 and k is equal to 3? Quadratic versus cubic nonlinearities. Well, I was telling you about our enemies for the Strickhartz inequalities, and those enemies are wave packets. And then I was telling you about what happens when you look at nonlinear interactions, and the interesting nonlinear interactions are resonant. So by extension, the very worst scenario is when you have self-interaction of wave packets. So that would be the worst enemy that you could have in this game. Self-interaction of wave packets only happens for cubic nonlinearities, because if you add two vectors, you're not going to get the same vector unless it's 0. Okay? But if you add 3 vectors, you might get back on your curve, maybe get back to your vector, because you have the plus and minus signs having to do with complex conjugates. So in the case when the homogeneity k is equal to 3, we see this worst case, if you want, self-similar, resonant self-interaction of wave packets. And so, in essence, for everything that I'm going to tell you from here on, I'm going to fix k is equal to 3 to capture this worst case scenario. And there's more reasons to choose k is equal to 3. We wanted to formulate some conjecture. As you'll see a little bit later, our conjectures, in the case k is equal to 3, are universal. They apply to very general classes of equations without having to get into the specifics of those equations. On the other hand, for k is equal to 2, trying to even make a prediction has to do with the exact dispersion relation and with the exact bilinear interactions that you might see, resonant bilinear interactions. So it gets very, very intricate. And fact of the matter is we don't have a prediction for that at this point. Not even if there's any chance of getting this global solutions. But if you're still disappointed of not hearing about k is equal to 2, there are some cases when you can turn k is equal to 2 into k is equal to 3. And this certainly happens for many problems that have been studied along the years. One way to do this is by using what's called normal form methods. And here I'm using the expression normal form methods very broadly. And this happens only if your problem has no resonant interactions. And then in some other problems that we're interested in, perhaps you might have some resonant interactions, but the amplitude of these resonant interactions turns out to be 0. And that's what that means that your equation has a special structure, and that's what we call a null structure. So algebraically, by looking at the dispersion relation in here, by this analysis here, you do have resonant interactions, but the strength of those resonant interactions is 0. So resonance exists, but their strength is 0. Okay, and I was told that if there's a good stopping time, we should take a 5-minute break. So now could be a good stopping time because we have nailed down this k. All right, so let me get back for a second to this heuristic here, where we try to figure out what k we should look at. And I started from the Strickhartz inequalities, and that's cheating a little bit, because that makes the presumption that the worst case scenario happens. And so far, I hope I persuaded you that the worst case scenario happens only when I have the triple self-interaction of a single wave packet. And maybe the other thing that I should have said is that this only happens in the case with phase rotation symmetry, because you want to see the algebraic relation sigma minus sigma plus sigma goes to sigma, not plus 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 or plus minus minus. This is the guy that corresponds to one frequency self-interacting with itself, giving you the same frequency, right? So, consistent with this, I wanted to show you another heuristic about identifying this worst kind of interaction, and that has to do with what happens when a wave packet interacts with itself, right? So we looked at wave packets linearly. Now we want to look at wave packets non-linearly. And so we take our equation. And now here I'm going to put a cubic nonlinearity with the phase rotation symmetry, u bar, and u. And don't worry. And perhaps now I can emphasize something that I did not mention before, but which is important. The equations that we're looking at are equations which are invariant with respect to translations, right? So you don't see any x in here. This trilinear form, if I translate it, is the same trilinear form. I was asked a few times, we were asked a few times, both me and Mihaela, whether we know how to do stuff when you don't have translation invariance. The answer for now is no. All right, so we have this equation. We take our initial data, u0, which was our wave packet data, our coherent state initial data. Psi naught. And now I want to understand how the solution here looks like. And my frequencies are all equal to psi naught. So how does the nonlinearity look like? Well, first of all, how do I describe a trilinear, a multilinear form, which is translation invariant? Well, I have to describe how different frequencies in here, and in here interact. So given a trilinear form, C of u, u bar, and u, which takes maybe three frequencies, psi1, psi2, psi3, to frequency psi1 minus psi2 plus psi3. All right? And I want to show how these three guys interact. And I describe this using what's called the symbol of this trilinear form. So this is, from here we get the symbol C of psi1, psi2, and psi3. So any such form, we describe it by its symbol, and this symbol will play an important role in my story. So this is the same way as multipliers. We describe them by a function on the Fourier space. Here, the symbol for a multilinear form is a symbol on a product of, in our case, 3 copies of the Fourier space. All right, and now all of these guys will be localized. I expect solutions to stay localized around this specific frequency, psi naught. So at leading order, my nonlinearity, I think, should look like C of psi naught, psi naught, psi naught, times u, maybe absolute value of u squared. All right? So now I'll try an ansatz for this evolution. And my ansatz was the same one that we had before. U of x and t is phi. Now I'll let this depend on time. And then lambda times x minus x0 minus v sine 0 t. And this was our xt, the center of the packet at time t. And then times e to the power I proper phase. All right. And I take this and I plug it into my equation and ask what happens. All right. And the linear effect of the flow is already taken into account the moment we do the transport and we choose the proper phase. So this means that there'll be nothing else to be seen in here. And what we get at the end of the story is an amplitude equation equation of the following form: phi dot. This dot means derivative with respect to this time variable in here is equal to, and what we're going to see in here is c of psi naught. Well, there's the I from I dt. Okay, so this is c of psi naught, psi naught, psi naught times phi times absolute value of phi square. And now we want to interpret this very simple ODE. You all know how to solve it. Simplest observation: if we want solutions of this guy not to blow up, then in finite time, then we should better have this C to be real. Okay? So, first observation, critical condition is C of psi naught, psi naught, psi naught. Leave some space in here, belongs to R, only when the frequencies are equal. You could be generous and say, oh, the symbol is always real. But the better thing to do, rather than being so generous, we were a little bit generous in the first paper that we wrote, but then we decided there's no point to that. The better condition is to say, well, I also look at the gradient of C, also at psi naught, and psi naught. And we ask for both of these guys to be real. So at the quadratic level, the symbol C is real on the diagonal. All right? And we call this condition conservative. This might say it's a little bit misleading. When you say conservative, you might say, oh, there's a conservation law. There's no conservation law. This is just that leading order somehow. Your equation is conservative. All right? And so for us to have any chance of getting our desired global solutions, we should better assume that our nonlinearity is conservative, right? And then the other thing that you observe, now assuming C is real, you can explicitly solve this equation, and you get phi of t and x is equal to phi 0 of x e to the power I t c of psi naught, psi naught, psi naught multiplied by phi square. Now phi is a function. It was a Schwarz function to start with. Maybe this also should be a Schwarz function. But if this is a Schwarz function, then the important observation is that it is not constant. If it's not constant, this means that as t grows, then this phase in here begins to oscillate. But the moment I let this phase begin to oscillate, then I'm changing the frequency of my packet. But if I'm changing the frequency, I'm pushing the packet to move in different directions. So it's not going to perhaps stay coherent, right? So the better computation to do to decide when is the nonlinearity stronger is to compute the time scale at which this becomes effective. When does this become stronger than the linear effects? And then we know that for wave packet initial data, we're going to see first the nonlinear effect before we see the linear dispersion kick in. So the question that we ask is, when does this dominate linear effects? And it's a little bit of a computation, but I wanted to show you this computation because it's really not so hard. One thing that I was telling you is that when we look at this wave packet in here, and I should have put here, maybe I forgot about x naught, okay, lambda x. Well, actually, we're okay as it is. But this gets applied to lambda x. It doesn't change the equation, but all right. I was telling you that this wave packets correspond to the frequency scale delta xi, which is lambda, right? So the question is, when does this phase promote frequencies which are larger than lambda? Now, what is lambda? Was a parameter, right? If I allow lambda to be large, then I have to worry about large frequency behavior. I don't want to go there. So this means that I'll have to keep my lambda small. Okay, so lambda is our new small parameter. Bad notation, but I don't want to change it midway. All right, so we have a small parameter lambda. And now I want to look at the gradient of this function. But before I look at the gradient of this function, I need to look at the amplitude of phi. So our initial data, imagine that it's localized at frequency psi naught, which is comparable to 1. So we don't have any frequency factors in there. And then I have this factor in here. And it's a Schwarz function. So what is the amplitude of this guy? I want the L2 norm of this to be 1. Okay? So the amplitude, maybe phi, should be like lambda to the power n over 2. Dimension over 2, right? It's going to be a very long bump because of this lambda factor. All right. So this means that if I'm looking at phi square would be lambda to the power n, right? But that's not what I care about. I care about the gradient of this. That's the frequency. So what is the gradient of t times c of psi times phi square? Well, so this is like obviously t. This c is 1, because we're at frequency 1. Okay, approximately 1. Phi square, this is like lambda to the power n. Okay, 2 phi's. And then I have this gradient. The gradient applies to a function that's stretched to the lambda scale. So this gives another lambda factor, right? All right, so this tells us that the important number in here, the time scale of this effect, if you want t nonlinear, will be, did I do something wrong? Hold on. Right. So what do I compare this with? I compare this with the range of frequencies that are allowed, right? So when is t times lambda to the power n plus 1 equal to lambda? That's what would give me the nonlinear time scale. I want to equate this with my original range of frequencies. And so I get this nonlinear time being equal to lambda to the power minus n. Right? On the other hand, the linear time, which hopefully is on that board, okay, is lambda to the power minus 2. So t, the linear time scale for the wave packet, is lambda to the power minus 2. And now you can do the comparison. They are equal in dimension 2. If you're in dimension 1, the nonlinear effect comes first. If you're in dimension 3 and higher, the linear effect comes first. And that's consistent with the computation that I did using the Strickard's estimates. So it's good if you do the computation 2 ways and you get the same result, it has to be right, yes? Frank has some doubts. It also has happened to me. All right. Okay, so next board will be drawing some pictures again. So we have figured out that if you're in one dimension, the nonlinear effect happens first. What does the nonlinear effect do? Well, it changes the phase of your packet, and then it promotes the motion of the packet in different directions, right? What are those different directions where the packet is moving? Well, you have three possibilities. Well, two possibilities. Depends. The third possibility is c is equal to 0 when it does nothing. But the other two possibilities is when your problem is defocusing, where you have the linear pattern, your linear wave packet, and then the nonlinear wave packet, nonlinear effect happens sooner, and the nonlinear wave packet will make your wave enlarge, right? So it spreads out. And then you have the focusing mechanism, which is the opposite to this. Again, you have your linear packet, and then the extra phase that you are promoting in there is going to make your packet contract. Is it going to contract forever? Not necessarily, but one possibility that could come out of this is that it contracts up to some scale where it sits put, and then you get a soliton. So one special case of this is you get a soliton, or a solitary wave, or depending on the context. All right, and if we want our global solutions to disperse, this is an enemy. All right? So whatever conjectures we make about global solutions, we want to exclude solitons because they're not going to disperse. Which means that we have to ask that our problem is defocusing. All right? Now, you look at the problem, where is it? Like that. Not like that, like this. What does it mean for this problem to be defocusing? How do we read this? Well, we want to have, for instance, defocusing effect on this packet centered around psi naught. All right? And this leading order effect, the sign, if you want, of the gradient of this, depends on the sign of C. So the sign of C is crucial. And so you do a little algebraic computation, and you decide one sign of C is focusing, the other sign of C is defocusing. So the way I set up the notations, assuming that A is convex, then C of psi greater than 0, this is defocusing, and C of psi is less than 0, this would be focusing. So what happens if I give you a more general equation? Not with the cubic nonlinearity. The nonlinearity is hidden in some complicated expression, right? You take the nonlinearity, you take an expansion of the nonlinearity, you take the cubic part of the nonlinearity, forget for a moment whether your problem is semi-linear or quasi-linear, just take the cubic term in the nonlinearity, you evaluate its symbol, and you look at the sign. That's what's going to tell you whether the problem is focusing or defocusing. Now, when is this important, focusing versus defocusing? I have made the case that at least in one dimension, this should be important, right? And the secret in one dimension is that you can get small solitons, so to speak. And so those would be an abstraction. But if you go to 2 dimensions, then the linear and nonlinear balance, and even if you have a soliton, that soliton cannot be small. So in 2 dimensions, you don't expect small solitons, which means that in 2 dimensions, perhaps you should care less about defocusing and just about the fact that your nonlinearity is cubic. All right. So far I have described how dispersion works and what are the important mechanisms for nonlinear interaction in our context. And before I state the conjectures, let me start with one brief sort of history of finding global solutions, very brief. So there is global solutions for small data. And the easiest way to get global solutions is when you have a conservation law where you have local well-posedness. Of course, you have to have local well-posedness in whatever your energy space is, and then this gives you global well-posedness. Time-honored strategy. But what's missing in here is you don't get any information about the global behavior of the solutions. Your solution is made out of little bits, all of equal time intervals, maybe, and you can describe each of those bits, but not what happens when time goes to infinity. A second scenario, and this doesn't go back quite into the mists of time, but maybe the 80s, okay, is when you have Strickard's estimates, and you can use the Strickard's estimates to run a contraction argument. And this applies nicely for semi-linear problems. The reason this applies nicely for semi-linear problems is that for semi-linear problems, all you need is the Strickard's estimates for your linear flow. On the other hand, if your problem is quasi-linear, there's no good way of getting sharp estimates, sharp Strickard's estimates for an infinite time. So this story is out for quasi-linear problems. Okay. Maybe the third scenario in here is when you say, well, perhaps my nonlinearity is too strong for any of this to work, and then I try to choose the best possible data there is. And the best possible data there is to choose small, maybe smooth, and localized data. So my data lives in a little ball in here, and linear waves tend to spread out in various directions, and there's decay. So as the nonlinear effect begins to kick in, this decay is manifest, and so you can try to take advantage of it. And of course, many of you know the very long story here. Maybe to mention some names for the wave equation, work of Kleinerman, Christodoulou, maybe for Schrödinger type equations or also waves, Lindblad and Sogg. So we're not yet into the 90s. Alinak, one of my heroes. And maybe I should also add Jean-Marc Delort. Made lots of contributions here. And this list should go on and on and on. People in the audience here also have worked on lots of problems like this. Thomas, about 10 of you, I think, at least. I forgot Ginibre and Velo. Yeah, but I cannot put everybody because the list would go into hundreds, I think. So I would not do justice to this subject. One thing I wanted to mention, at some point, maybe about 3 years ago, after a summer school together with Mihaela, we wrote some expository notes that are in the AMS transactions. Okay, so if you're curious. And so that brings me to our problem in here, where we want our initial data to be small, but we don't care about it being smooth. So we want our initial data to be potentially rough and not localized. So here you have waves coming from anywhere, going to anywhere, interacting at any possible time and at any possible scales. All right? And so we're asking, can we get global solutions in this context? Can we make a prediction for a good class of problems? All right? And so now we're getting to to the two conjectures that I want to. Well, there's more than two, you'll see. But maybe the most important is this first one. So this is from 22. So it says the following. We have a 1D dispersive problem. Cubic means you could still have higher order terms. We don't care so much about the higher order terms. Conservative. With phase rotation, symmetry, and defocusing. So I just made the case that cubic is important to get the worst interactions. Conservative, we need it in order to avoid immediate blow-up. Phase rotation, that's a different story. This is to make the conjecture as general as possible, if you want. So for specific equations, you can try to remove this. And the conclusion of this conjecture is that in this case, we have global well-posedness for small data. And these global solutions that we hope to find would be, let's call them global dispersive solutions. I'm using the word dispersive in here as an alternative to scattering, and I'll explain in a moment what we mean by this. All right. But maybe before I go on, as you see, this is a conjecture that applies to lots and lots of equations.
Maybe the data should be in HS?
Data, small data. I should have put small data. HS data. So you measure smallness in your favorite Sobolev space. And of course, as we started, would have been happy to get some result in any S. But the moment we started looking at specific problems, then we got a little bit greedy and wanted to get the best possible S, hopefully a sharp S. Okay? I'll tell you more about this in a moment. All right, so this is our conjecture in one dimension, and hopefully I have motivated it sufficiently. All right. So now we go on to, maybe before we go to the two-dimensional case, one obvious question is what happens if you look at focusing problems? Is there a counterpart of this conjecture for focusing problems? And of course, for focusing problems, you cannot hope to get any sort of dispersive decay at infinity. And then once you allow a soliton into the picture, then silly things could happen, like blow up and so on. Maybe you have more than one soliton. Maybe you can move along the family of solitons, as many of you have worked on. So you can ask still, what is a reasonable focusing conjecture? So 1D, again, dispersive problem, cubic, conservative, phase rotation, remove the defocusing. And then we say we have O of epsilon, HS data. So now we try to quantify the size of the data by some parameter epsilon. And then what should be the conclusion? We cannot get global solutions, but what we hope to get is O of epsilon to the power minus 8 lifespan. And we have some clue that this epsilon to the power minus 8 should be sharp generically. But this would take much more to explain. All right? So this we think, is the really important number over here. So this is the second conjecture in one dimension. We're not assuming that the problem is focusing in here. So this applies regardless. Maybe it's of mixed type. Maybe in some regions it's focusing and in some regions it's defocusing. That's what we would hope to do. But of course, the bad action would happen in the focusing case. And then if we go to higher dimensions, all right, then the cubic nonlinearities are critical. So semi-linear problems should be easy if you give enough regularity. So here we're going to look at quasi-linear problems, so we'll make it hard. So dispersive quasi-linear problem, cubic, and we stop. And then we have small HS data. And the conclusion here is that you have global well-posedness for small data. And we have scattering solutions.
Do you expect in the very first case modified scattering generically?
I'm getting to that, right? So here I use the word dispersive, and here I use the word scattering. And now I want to explain, that was my next point, to tell you what is the difference between this. Let's see, I think we're done with wave packets. Wave packets are good for intuition. Somehow we never used wave packets in arguments, in proofs. But you know, it's best if you know what your enemy is, so that your estimates are prepared for your enemy, to defeat your enemy. So let me begin with the two-dimensional case, which is more classical. So there, we'd like our solutions to be scattering. What does it mean? Scattering means that if I'm looking at the flow back of the solution at time t, or maybe I'm looking at the solution time t, and I'm comparing it with the linear flow of some initial data, let's say u plus, this in HS goes to 0 as t goes to infinity. All right, so this is the most classical scattering. Your solution at infinity looks like a linear solution. What's slightly different here from maybe what you have seen before is these problems are quasi-linear. So if you look at the map from u0 to u plus, all you can say is that this is maybe a continuous map. But you cannot say that this is in any way a smooth map or Lipschitz continuous or whatnot, like in any quasi-linear problem. The other thing is when you, in the more classical theories for dispersive equations, you try to put your functions in Strickard spaces. And so you can ask the question, are these solutions that we expect in 2 dimensions, do we expect them to be in Strickard spaces? All right. And in particular, if you were to put your solution in L4 space, then you might have some room for perturbation theory. But of course, again, the problem with quasi-linear, and proving L4 estimates without loss seems to be out of the picture. Still, what we hope in the case of 2-dimensional problems, we expect that we will have maybe L4 bounds with loss of derivatives. And if you're expert, I can give you an exact number, 1/2. All right. And then we would also hope to have bilinear L2 bounds. All right, now we go back to n is equal to 1, which we expect it to be worse. In n is equal to 1, there's no scattering. The reason there is no scattering is because you have wave packet dynamics which become nonlinear and don't relax at all to something linear. If you have problems like I mentioned here with localized initial data, then you might hope for some modified scattering. This is also out of the picture because your bad action can happen at any place and at any time. So there's no modified scattering either. You can make this a theorem. Still, you have to get something, right? And so what we hope for n is equal to 1 is instead of classical scattering, maybe we define dispersive to mean that you have some L6 bounds. And from our experience so far, depending on the context, there might be with or without the loss of derivatives. Okay. And then we expect to have this bilinear L2 estimates. Now, when I talked about bilinear L2 estimates in the linear case, it was very clear what that meant. You take two solutions where the Fourier support of the data are separated, and then the bilinear L2 follows. What does it mean in the nonlinear setting? Because well, waves don't stay where you put them. They tend to move around. So this means that I take my nonlinear wave, I chop a bit of it in some frequency region, I chop another bit of it in some other frequency region. I do this chopping at all times, right? And then I take the bilinear estimate, and I hope to get that bilinear estimate is in L2. So this is something like PA U times PB U bar. Norm of this in L2 is smaller than something that depends on the data.
When you say you don't have modified scattering, you mean because the approximated dynamics in modified scattering is well defined for data in HS, right? It's a well defined object. You know, when the data is localized, you have modified scattering, and the approximation is well defined for HS initial data.
You could say, you mean you start with HS data and you approximate to the localized data?
I know what is the good approximation for localized data.
Okay.
And then it looks to me, if I'm not mistaken, it's well defined for HS initial data.
It's not. I don't think it's well defined for HS initial data, and that's because you can split your HS initial data into bits, and you can have these bits very far apart from each other, right? And you can have these bits concentrate at very different times. So the picture that you can imagine is maybe I have my time 0, and within my solution I'll see perhaps some wave packet. This is some nonlinear interaction, which comes from some piece of the data, and then it spreads out, right? And then maybe somewhere else I'll have some other, let's say, wave packet, and things are very nonlinear around this guy. So you don't have any good linear approximation.
I don't say linear, but the nonlinear one, if you write in the Fourier space, it's something, the Fourier transform of the data times some oscillating factor. This is in HS, right? Okay, we may discuss that.
We can discuss this, but the contention is that there is no scattering or no modified scattering possible in this context. All right. So we have these conjectures, and then I wanted to give you a very brief overview of the work that we have done so far. And then in the next lectures, I'll try to get in some of the details about how we go about proving this. So let's see. Maybe I can use this board. So let me begin with results in one dimension. And I'll say our initial favorite was Schrödinger type equations. And this has to do more with the tools than with the results. And so our first problem in one dimension was to look at a semi-linear Schrödinger equation. Very simple cubic nonlinearity, translation invariant, phase rotation symmetry with all the hypotheses, so the conservative, the defocusing assumption. And so we looked at this in L2. So we prove the conjecture in L2. And then might be a little bit surprised about our assumptions on this symbol C. We don't really assume any symbol type properties on this. We only assume that this is bounded and has bounded derivatives of some order. So C is C in all the three Fourier variables. And of course, it has to have a sign for the defocusing condition. All right. So this is the first result in one dimension. And this is a semi-linear problem. But when we started thinking about this, our main target was quasi-linear problems. So we instantly went to the next example, which was a quasi-linear problem. Can we do this for something where we know that linear tools don't really work at all? So our second example was still a Schrödinger equation, but the quasi-linear Schrödinger equation. Here I should have put dx2 if you want. So here's some nonlinearity depending on u, maybe du and du. Again, phase rotation symmetry. So maybe I should put a complex conjugate somewhere in here. This g obviously has to be real, positive. So g of 0, let's make it 1. Okay, we're looking at small solutions, so g will remain uniformly elliptic if you want. And so here we're looking at this problem in HS with s greater than 1. All right, and so our result again says that we have global solutions, and the global solutions satisfy those dispersive estimates, the L6 estimate and the bilinear L2 bounds. And I'll tell you a lot more about this. Maybe you'll hear more than you want to hear about those next week. All right, so that was our second example. And then, well, that was already too much Schrödinger, right? And what we really wanted to get to was different dispersion relations. And this only happened, so this was in 22. This was in 23. This was in 24. Different dispersion relations. That means that we have our equation I dt plus A of d u is equal to C of u bar and u. So we gave up something. We make this problem semi-linear. But we win something in the sense that we have this A of d, which is now an arbitrary dispersion relation, which is fully dispersive. So just to get an idea of what happens, we look at the second derivative of A. We're assuming that A is convex, and we're assuming that that this is like C to the power gamma. All right, some power. And this gamma, in the results that we proved in this paper, is just about everything except for -1. -1 is a bit of a peculiar number. I don't know if you like or you don't like -1, but and you might ask what equation corresponds to that. That's the SQG front equation. So we're trying to do that now. And then we have some condition on this C, and now we made things simpler, and we assume that C has a symbol type regularity. So you could think of this C of C, and C, 1 to C3, to be something like C1 to the power delta, C2 to the power delta, C3 to the power delta. Not exactly this, but something with the same symbol type properties, and again, defocusing, and with a range of delta depending on gamma. The fun part in here, I wanted to brag a little bit about that, is the following, that so here you can come up with some critical Sobolev exponent in the high frequency limit. Okay, maybe not the low frequency, but at high frequency, because of this gamma, you have some scaling. And so the fun thing here was that we are able to assume that norm of U0 in the critical Sobolev norm is much smaller than 1. So the only assumption that we make on the initial data is that it's small in the critical Sobolev space. And the silly thing here is we have no idea how to prove well-posedness at this setting. We can prove well-posedness at some higher regularity. So we take more regular data, but we assume that the data are small in a critical Sobolev norm, and then we get these global solutions. So still something to be understood there, because when there's a gap like this, somebody is going to try to narrow it, right? It's a fact of life. All right, so this is 1D, 1 minute left. 2D, the first result, that's also 24, is the quasi-linear Schrodinger equation, dt plus gij of u, di dj u is n of u du. And here, again, we work in HS, and S is greater than n plus 1 over 2. Incidentally, we believe this is sharp. We believe this is sharp.
N equals 2 here.
Plus. Except maybe for the endpoint, that's something for an enterprising graduate student. Well, we tried to do S is equal to 1 here, didn't quite work out. But there's hope that maybe it will work out in the future. So this is A, and then there's B, and this is the thing that will happen next week. We take exactly the same equation, but with the difference that here G was a positive definite metric, right? Here everything is the same, but here we have what's called ultra-hyperbolic case, where the signature of G, where G does not have a signature. You might say, well, this is maybe a small variation of this, and in fact, it's not. And if you look at all the examples that I gave you, this is actually the first example that we're able to prove this conjecture where the dispersion relation is not convex. And working with a non-convex dispersion relation is some headache, which is why this has weight. Of course, you cannot have in one dimension uniform convexity, uniform dispersion, and non-convexity. So one dimension, you're stuck with convexity, or you have to allow for degeneracies. But in 2 dimensions, there's lots of interesting examples that maybe some of you have worked on, where you do not have a convex dispersion relation. And so everything is work with Mihaela. This last paper would be work with Mihaela and one of my former graduate students, Ben Pinot. Okay. Okay, and I think I'm out of time, so it's perfect time to stop.
I'm a little curious to see what are the global dispersive properties in the simplest case A. So you take cubic NLS with maybe some bounded nonlinearity. What kind of global dispersive solutions do you get for just L2 data?
This is the L6 bound.
Yeah.
So no derivatives. So this is no loss of derivatives here. And then the bilinear L2 estimate is exactly the one that I put on the board at the beginning.
All right. Thank you.
Other remarks, questions?
I have a question because I will not come next week. Sorry. So you mentioned that you make all these things around Moravec, focusing to at the end solve some low regularity problems.
Mm-hmm.
So how it compares with the best technology for low regularity problems like the short time Fourier restriction method? You are a part of the people who invented. Can you come back to other quasi-linear problems where, as you remember, there was a lot of...
That's a lot of work in progress in that direction, but the immediate comparison that I can make is for this quasi-linear Schrödinger equations, where I have worked on this in the past, maybe 10 years ago, with Jeremy Marzola and with Jason Metcalf. And we had some results in HS spaces, local well-posedness, and our local well-posedness was one derivative higher. So we improved those results by one derivative. Obviously, we didn't know the best technology at the time, right? And like I mentioned, and maybe I'll get to explain a little bit more next week, we believe these thresholds are sharp, generically.
So you believe this kind of method will be better than this short time analysis and things like this?
I think so, yes. Definitely so for these problems. But I can say one more thing. This is actioning happening in Rn, right? And the short time works in also other contexts.
So will you survive at least in this context?
So just a very basic question. Okay, yes. So you are arriving to the critical level here?
In one of the examples, in this example here.
Yes.
This is the only one, actually, of these results where we arrive at critical level. Here the scaling is -0.5.
And, but at the critical level, do you think it's still reasonable to do it exactly at the critical level for the best?
What does it mean to do it? I mean, you cannot do it.
You have done it for the critical power, let's say, or plus. Plus epsilon or epsilon equals 0.
There's, as far as we know, there are no results of this type at the critical level in this context somehow.
But you think you base hope or not? No. Okay.
Maybe.
No,
in the distant future.
Yeah, using the specific.
Right. So of course, one particular class of examples in here, maybe I'll also say more about that next time, is you can look at integrable models, right? And for integrable models, you can say more. But one of the things we're trying to do here in terms of global solutions, we're taking integrability out of the picture, right? We're looking at models which are general enough so that there's no integrability whatsoever. So it's only the leading order structure that matters.
Very good.